Hello everyone, welcome to my YouTube channel. Thank you so much for your amazing response and awesome following. You all know I started this podcast series mainly related to health education and lifestyle. So today we are going to discuss about quantum computing and that too about a very interesting topic. I request you all to listen to this interesting topic from an eminent expert. You will definitely get to know all the pointers regarding this topic. You may use it for your project works, you may use it for your research work, and also for further growth in this quantum computing area. To start this topic, I'll just tell you a few pointers. Have you ever wondered how a slight change in wind temperature can decide whether a day turns out sunny or stormy? Today's episode is about mind in motion, where we explore the strange, beautiful, and unpredictable world of chaos theory and how it might just hold the key to understand everything from the weather to your mood to the future of quantum computing. Chaos theory sounds wild, but it's not about randomness. It's about pattern hiding inside the unpredictable. It tells us that small changes in initial conditions can lead to massive, often unexpected outcomes. Today we will explore what chaos theory really is and why it matters beyond science. Not wasting your valuable time, we have an eminent expert, none other than Daniel, who has done his PhD work in the area of chaos theory and is also acting as CTO. He is also quantum solution officer, enterprise architect, and senior IT architect. He has done several excellent roles in the area of quantum computing. Thank you, Daniel, for accepting my invitation. Can you kindly introduce yourself?
Thank you for introducing me, Rajesh. I will shortly introduce myself, but you told most about it. I am the chaos theory PhD. That's a great part of mathematical analysis, one of the most complex ones about it in mathematics. I am the student of Michal Fečkan, who is for consecutive 2 years among the 1% of the most cited mathematicians in the world. So he is a great capacity itself, and I am lucky and proud. I am a lucky and proud student of him. During the last 25 years, I am mainly focused on the field of applied mathematics and applied IT. So I worked through lots of projects in IT that span data science, data architecture, artificial intelligence, and for now I am pioneering in the field of quantum computing and quantum artificial intelligence. As they now turned from the one day, possibly coming to its day one. They are entering their day one in our society. So it's really great times to be in quantum computing and in middle of everything what's happening now with my knowledge stemming from chaos theory. So thank you for having me. That was a short introduction.
Thank you so much, Daniel. Can you please talk about the recent Nobel Prize given to the 3 scientists in the area of quantum computing? It is a great news for the entire world of quantum computing. How do you see that?
I see it. It's very nice. We couldn't find a better time because it's for me it's a Nobel Prize for quantum bit for qubit. Especially for Josephson junction, superconductive qubit. And in superconductive qubit, it's a mixture of combination both quantum effects and both chaotic effects. And it acts also as a damped pendulum and also as a quantum system. And in fact, the problem of one of the problems Nobel Prize was awarded for was the mitigation of that chaotic pendulum-like probability that occurs here. And I'll show you something. This is my diploma work from 1995.
Okay.
It's in Slovak, but it's about bifurcation of bifurcation of rotating pendulum, and what's in there are some Hamiltonian functions and some pendulum functions that are really common with what is acting, what is happening in Josephson Junction. So for me, it's a nice story because it's where chaos meets the quantum. But here, chaos is the one who has to disappear. And the people who was awarded for Nobel Prize were really acting to make from Cooper pairs basic quantum bits, trying to mitigate the chaos, that pendulum-like behaviors, to make from it a transmont qubits that are much more stable. And for me, it's the best what can happen for quantum computing community to award these people with Nobel Prize. So good luck to them.
Exactly, Daniel. I do feel the same. We are very happy. Daniel, what exactly is chaos theory, and why should everyone, even outside the science, care about it?
Chaos theory is extreme sensitivity to initial conditions. So we will make small difference in where we start, and we will end completely at the other side of the results will be extremely far apart from each other. Why to care? Because the chaos is in every system that we have. Systems are what I am expert in, and how we can describe the systems. We describe them as a dynamical systems. And most of dynamical systems are nonlinear one. Nonlinear systems are chaotic by its nature, and it means that from markets, whether supply chains, organizational processes, and so on, everywhere is chaos. So we can't, and chaos learn us, taught us that we can't forecast can't forecast with the special right, with the right conditions, but we can see some patterns, and through that patterns we can predict what will happen on the something like high level from the roof. So we are able to see even when we are not able to explicitly compute the result. We are through the chaos theory, we are supposed to make a really good forecast for what will happen.
Okay. Can you give us a real world example of chaos? Something from daily life that perfectly shows how small changes can create big outcomes. Any real time example?
I'm a skier, so the best example I know is an avalanche. You have snow, and the snow is quiet, he's lying there, nothing happens.
Yes.
Small amount of some energy or some fluctuation of some change can make a big difference. Avalanche is going from the hills, and you don't know where it will end, whom it will hit. So this is the best, and in fact, the avalanche-like processes are wherever around us we can see. So in technology, there are processes like avalanche where small amount of energy will come to the extremely different results. In fact, we see it now because now is the rise of AI. The rise of AI made total disruption of the world around us. And in fact, it's a small amount of people thinking about some new pattern, how to compute something. And it has this impact on the whole society. Yeah.
Yeah. How this chaos theory helps us understand complex systems like weather, economy, or human behavior?
Like I said, it shifts our goal from predicting to mapping. We are able to create maps that show how the system will change in the time, not how the system will exactly look like. So that is prediction, but we are able to map where it will be in some intervals where we can find it. And those intervals, once created well, can really show us. They will prepare us for future, for some events that will occur in future. We don't know how exactly those events will look like, but we can map the system that they will occur. Yeah. So this is exact shift where and you can't use, as we are not able to explicitly compute, we can't use other systems like other theories like chaotic one. Then the chaos theory is the right tool for the thing.
Okay. So now let us connect the dots, Daniel. Where this quantum computing meet with chaos theory? Are they similar in unpredictability or completely different worlds?
They meet in one word. They meet in word probability. There are two types of they represent, both of them represent two types of probability. Quantum represents what I call intrinsic or ontic probability. It's something that is deeply rooted in the nature itself. So deeply inside the nature is probabilistic, the quantum way. And on the other side, chaos is probability that arises from change. When we are going to achieve something or move something somewhere forward, the chaos occurs as something that looks that harms this process, but in fact it supports it. It supports it with something like free energy. And that free energy we can use, we can borrow for our going forward process is called chaos. So this is support part of the moving forward. And in fact, there is also historic part of what connects chaos and what connects quantum. For where the first where chaos arose was so-called Rayleigh-Bénard convection. It was about heating a tank of water or fluid with metal plate from the bottom. And scientists expected that more heat will come. The fluid will boil in the more chaotic way. In fact, that experiment showed the first synergy or chaos pattern where at some point the fluid couldn't create more noise or more chaos. So it started to show the pattern of hexagon where the boiling water was going up through the hexagon and was falling down, creating hexagon-line pattern. And it was where chaos arose. Then Lorentz made that attractors and that butterfly effects, and also it was then. But interesting that it's called Rayleigh-Bénard connection. And Rayleigh is that lord from the Rayleigh-Jeans law that was in standpoint of black body radiation, where Planck resolved it with quantum. So Lord Rayleigh connects both chaos and quantum in a way. And now the quantum and chaos are connected in history through the Nobel Prize, as I mentioned before. So there is a deep connection between those two theories of or tools, or call them whatever we want.
Exactly. Well explained, Daniel. Can you please let us know in simple words how this quantum computer actually process information differently from a normal computer?
Now I am mathematician, and
Yes.
now I'll be maybe little controversial, but I'll tell it. I'm a mathematician, and we have the third theory that is going along with quantum chaos and so on, and it's Gödelian one, Gödel and Cantor and uncountable infinites, and in fact, from them comes to me that quantum, that superposition and entanglement are interesting part, that we can't create nature without superposition and entanglement, and that affects how quantum computer processes information, because superposition is about not being true or false in the one time, but being somewhere in combination of both of them. And the combination is even not in the real space, but in the complex Hilbert space. So it creates something like Bloch sphere, if you know, if for those who are new in quantum computing, you can compress it or transform it into Bloch sphere, and you can everywhere on the Bloch sphere you can use that point to do something in quantum computing. It's unbelievable, because in classical computer you can use only the north and south pole from the Bloch sphere. Okay. And it's more unintuitive, because most of the Bloch sphere is even from the complex space, which doesn't seem even real. So we are borrowing from something. We are borrowing some quality from the space that is unreal, and it's unintuitive. More unintuitive is the entanglement, where two particles or qubits, when we realize them, can be, no matter how far apart, they are one physical system. They obey one equation, and in that equation somehow there isn't that distance between them. The distance doesn't play their role. So you can have two photons far away, and they can act as a one physical system, what allows us to secure communication, to unimaginable patterns. And those two patterns, superposition and entanglement, are the ones that define that quantum computers are not the better part of current computers, but they are intrinsically new. It's great how Shohini Ghose is one of the people that are leaders of quantum computing, and he talks that she uses a nice analogy that you can build a light bulb by making a better and better candles. So current computers, classical, are for me like candles. But making progress in them, you will never make an electric bulb and never make funny things that are possible with electric energy.
Yes. So nicely told. You told very nice point, Daniel, that current computers are like candle. Yeah.
But sorry for those who are hearing. Don't hesitate. Current computers still have a value. Don't throw them from the window.
Yeah. They cannot do that. But yeah, that is a good point you have told. Superb. My point here is that can quantum computers help us predict or control chaos, or do they make the chaos even more complex?
Yeah, they can both of them. They can do chaos more complex, and
Uh-huh.
they can help us to predict, because it's how do you use the probability? Well, you can use those two mediums of probability, those intrinsic by quantum and those classical by chaos. We can use them to make to add and make more probability. So then the system becomes more complex. When they act together and they are multiplying each other, it's more complex situation. But in some you can use them that one of them mitigates the other. So
Yes.
helps to then helps to make some order in there. And their quantum computer is really interesting because his probability is more is deeper rooted. It's the intrinsic probability, so he is able to absorb chaos. That's why, in fact, that's what I plan to use, because one of my works you can see on the internet. Maybe we will put it also here on ResearchGate. You can see one of my works. It's really interesting. It's called extension of Euler identity via Feigenbaum constant, and I made it in Ramanujan style, as I like Srinivasa Ramanujan a lot. So I dedicated it to him and did it in quite in his style. But there I propose a system. Chaotic systems are bifurcating, coming to doubling their periods, and all of them obey such a fancy rule that there is a Feigenbaum constant. When you put the ratio of the next iteration against the ratio of previous iteration, every chaotic system tends to obey that Feigenbaum constant in the end after infinity. In limit, it goes there. And in my work, I predict the system that bifurcates exactly by Feigenbaum constant. So it's something what I try to achieve. It's something like find the circle. Circle is the perfect object when you are talking about pi.
Yes.
Yeah. Euler is perfect object when we are talking about differentiation and integration. And
Yes.
when we are talking about dynamical systems, which describe the nature around us and the society, then we would like also have something like circle that is going smooth and without having some incontinuations and disabilities. And I found that there is the possibility to find that system. There is a way. In fact, with the help of Michal Fečkan, I proved the first conjecture that system exists and is exactly one. And it's great. But to find that system, I propose that I will need quantum computer to use his, and it's in fact it's one of my main motivation to operate in the field of quantum computing, to try to find something that will help me to find that exactly great dynamical system that will exactly obey the bifurcation laws of Feigenbaum constant. So this is how quantum computing can help us to conquer the chaos. Yeah?
Super. What kind of quantum algorithms or mathematical principles could be inspired by chaos theory?
Those are optimizations algorithm. When we come to optimization some processes, then we can modulate that the processes are often described by differential or differential equations, and those equations can be somehow projected into the quantum space. The quantum space is richer as we have the complex, as we can use the complex analysis. Those are for those who are new with it. Those are the strange numbers coming from square root of -1 from I. When you try, and when we try to use these complex analyses, we can optimize that processes much more effective. So this is where mathematical principles can be inspired by chaotic theories, yeah, by chaos theory itself.
Okay. Daniel, do you think chaos could actually be used as a resource in quantum systems? For example, to improve randomness or security?
Chaos could rather be used as a way to govern those systems, because chaos with those simply deterministic equations, once we can give us the mapping. For example, once somebody will achieve the results I propose, will create that great dynamical system that bifurcates by strict laws, by strict pattern, he can then we would be able, once we will achieve this, we will be able to act as to set the parameters, and then system will act as predictable in terms of what will happen on the high level, on the roof of this. And then chaotic systems can in fact not be resources, but something like governance patterns. It's the same as the proper word is the patterns. They will be able to drive us through patterns of the underlying dynamical systems. Yeah.
Yeah. You are the person who is working with the intersection of data, AI, and quantum. So, how do you see chaos influencing the future of intelligent systems?
This is probably the best question I can get, because chaos is because I'm the mathematician, and as a mathematician, there is that complex space, and in complex space, functions obey one very interesting rule. If you have smooth function, I will not discuss here what is smooth, but it has every derivation and so on. Then there exists something like analytic continuation. From small area of solution, you can extend it to the whole area. And it means that when we will do in future artificial intelligence system, we can use this. We can use this to modulate just a small area well, and then extend. What's the problem is that extension obeys to the rules of chaos. So when we at that small area, if we will make a little mistake or in the wall extension analytic continuation, it will make a huge difference. So and that's where chaos meets artificial intelligence, and where it meets quantum. And we need quantum because quantum naturally operates in those Hilbert complex space. We need chaos to predict it, and then artificial intelligence will be really great at the level I want to see. In fact, I am doing with artificial intelligence for about 15 years. With quantum computing, I am working about 10 years. With chaos, I am for 30 years in chaos. Yes. And what's interesting, current classical artificial intelligence is great. Yes. There are only 3 words that are stopping it for now. That 3 words are resources, privacy, and comprehension.
Yes.
Resources I don't need, and all three of them, resources is backed by speed up of quantum computers. Privacy is backed up by quantum communication, which is security backed by the natures of law itself, by the laws of nature itself. And the third, which I am here most for, is the comprehension, the ability of systems not only give us the correct answer, but give us correct answers in the right context. And there those artificial intelligence built on complex or on analytic continuation and on quantum complex analysis shines. It's the place where it really shines, and that's why I'm fascinated, and why I am often talking when I'm in good mood that it's very good to be me.
Yes. Finally, Daniel, I wanted to ask, like, if we had to explain the future of chaos, quantum, to a 10-year-old small guy, how would you describe what's coming next?
Describe what's coming next, that to the 10 years old. The 10 years old example I love, because I often describe it like this. Let's suppose we are in the water park, the very great water park, and there is father and son. I have 4 children of mine, so I was in water park for lots of time, and you are there on the biggest tower with sliders, with water slides. There are a lot of water slides, and they are ending. One is landing on this side of the one here, and father and son are standing there. Father is looking for a moment, he's looking away, and his son decides to use one of the slides. But father doesn't know which. And this is chaos. This is chaotic process, because you will choose red or blue, and you will finish at the other in the other area of park. And then comes quantum. Once the father knows you, he can use quantum computing. Now I'm talking about something like Grover algorithm, and simply the water park and everything will disappear, and only father sees his son. This is quantum computing. It
Yes.
helps us to resolve, and this is really magic. So what is coming next? From my perspective, we are facing now the rise of the classical artificial intelligence. Classical artificial intelligence, from my perspective, has those 3 words, and those 3 words are serious issues for artificial general intelligence, for something that will be able to act in context. And there, from my perspective, the quantum computing with all the mathematics as chaos theory, as mathematics of complex analysis with analytic continuation, is really prepared to help. From my standpoint, as a mathematician, it's a bright future, and I see how it will happen. From the standpoint of us people, it's a lot of work before us. But I am enjoying where we are so far, and I hope we will make it towards. I would be really happy to live one day that picture that I have, that picture of future that I have now in my head. I appreciate it, and I hope we will be there someday, and I hope I will be alive to see it.
Oh, you will be definitely alive for so many years, Daniel. Yeah, and you will see that definitely.
Yeah, thank you, Rajesh.
So that was really nice, Daniel, Dr. Daniel, to talk to you. You are a great person, great innovator, and you have done a lot of work in the fields of data, AI, and chaos theory, which is your main field, and as well as quantum computing. And to have you here in this podcast and to talk to is a great privilege for me. And thank you so much for accepting my invitation and spending your valuable time with me. So nice to talk to you, Dr. Daniel, and you are a very friendly natured person. That is what I really like. Thank you once again. It was great pleasure to have.
Thank you for having me, Rajesh. It was also fun for me. Thank you.
Thank you.